Now let's have this letter E. So for this problem, what we have here is 3x over x squared plus 4 dx. Now the difference from the other one is that we have actually an x here instead of just having a constant. Now remember, in this kind of expression, you have to carefully look at the denominator for any rational expression. So why is that so? Because that tells you actually what you have to do in a certain expression, because this works differently when it comes to the numerator. Of course, I'm talking about the same denominator here, x squared plus 4. Now the difference here is that we have here something like 3x. Now when you see something like the highest exponent, which is actually x squared here, is basically the derivative of what is on the denominator. Because if you try to differentiate this x squared, what you'll be getting is 2x. Though this is not 2x, this is actually 3x. But the thing here is that if you will be trying to differentiate this, what you are supposed to be getting is the numerator itself. And in this case, it's just a matter of modifying the constant. But in this case, it exists in a way that the derivative of the denominator is the numerator, or something like similar to the numerator. So it's something like if the derivative of the denominator is kind of congruent to the numerator itself, then what you have to do is to look at the denominator and try to like find its antiderivative. Okay, so with this, knowing that the derivative of your denominator, so if you try to like execute differentiation to the denominator, we could say that this is actually 2x. Okay, and if this is 2x and we want to have this 3x, what we have to do here is to plug out 3 first. So I'll be having 3 and then the integral of x dx and then x squared plus 4. And then I want this certain numerator to become 2x. So I'll be writing 2x because I need that. So that makes this derivative equal to 2, something like 2x. Okay. And then I'll be writing the remaining terms. So that is x squared plus 4. Okay. So this is what happens. Now, if you try to make this 2x and then this is not equal, because this one is actually 3x dx, but this one becomes 6x dx. Okay, so by that knowledge, we know that since this is not equal, because this becomes 6x, we can actually something like neutralize, but that's not actually the perfect term for this mathematics, but we can actually take the reciprocal of what we have multiplied here, so that becomes 1/2. So we multiply 1/2 to the expression, so that as you can see here, what we did is not actually, we didn't actually change the equation itself, because you can cancel out 2 here and this leaves us with 3x dx over x squared plus 4. But in this case, we wrote this form because we can actually take the derivative of x squared plus 4 leading to 2x. So with that, with all of these changes that we have done, though it's not literally changes because we're not actually changing the equation here. So with all of this redefining, we can actually say that the derivative of this x squared plus 4 is this 2x, which is the numerator. So this makes perfect sense using our natural logarithm. So that makes this 3/2 times the derivative, the natural logarithm of x squared plus 4. Okay, and this is your final answer in this problem. Because if we try to differentiate this, so let us just check this by differentiation. So this gives us 3/2 times the derivative of, the derivative of x squared plus 4, so that is 1 over x squared plus 4, and then you multiply this with the derivatives, so that's 2x. So basically what happens here is that we're trying to express our integrand in a way that it fits to the rules. That's why we called it a fitting integrand. If it is not a fitting integrand, then we'll be trying to do a little redefining so that we can deal with the expression itself. Now remember, this is what happens when you try to differentiate the denominator, and then the derivative looks something like the numerator itself. Had this been 3 only, then you'll be applying the inverse trigonometric function or the rules, because the derivative of this denominator isn't something like congruent to the numerator itself. Now, what if instead of having 3x or 3, we have 3x squared? Now, to deal with this kind of integrand, we need to look closely at the exponents. So whenever you have a rational expression, the first thing that you need to do is to inspect the numerator and denominator. Now, I've mentioned before that if this is something like a constant, you will be mostly probably applying an inverse trigonometric function, given that, of course, this is squared and then a constant. And then if this is something like 3x, which is kind of congruent to the the derivative of the denominator, then this becomes something like natural logarithm of the denominator. Now, what happens when this one has the same degree of exponent as with the denominator? So if, let's say, if n is the degree of the denominator and then m is the degree of the denominator, then if these uh, degrees are actually equal, then what we have to do is to perform first the long division. Okay, so in this case, we'll be performing long division. Now, in this case, we have 3x squared and then divided by x squared plus 4. Okay, so in this case, we have 3, and then we multiply this, that's 3x squared plus 4, plus 12. Oops. Okay, so that is plus 12, and then we subtract this. So what we have here is negative 12, and then we cannot proceed any further, so we just have to rewrite this as the integral of 3 minus 12 over x squared plus 4. Okay, so this is our new expression. And this redefined expression is what is, it can be dealt easier than the one here before. And this is actually what we have to do when the degree of the exponent and the denominator and the numerator are actually equal. Okay, so let's do it. The integral of 3, which is a constant, so this becomes, we just have to copy the constant and then attach x, so that is 3x. Okay, and then how about this one? This one looks something like the one we did before. That's a constant, and then of course this one is the x squared plus 4, which looks something like the denominator of an inverse trigonometric function. So in that way, I can just copy 12 and then multiply this by 1 over a, because this one is the inverse trigonometric function of a tangent. So that is 1 over a, in this case that is 2, and then the inverse tangent of x over 2. So we add c, and therefore the final answer is we have 3x minus 6 inverse tangent of x over 2 plus c. Okay, so this is our final answer. Now we can always check that by differentiation, so I'll be using yellow again. Now we can have the first term, that is 3, and then minus 6 times 1 over the square of this function here, so that's x squared over 4, and then plus 1. And then of course we have to multiply this with the derivative of x over 2, so that's 1/2. Okay, then we try to simplify this by proceeding with all the necessary operations. So I think we have 3. Let me just continue it here. So that is 3 minus 6 times 4 all over x squared plus 4, and then times 1/2. Okay, so you can simplify this into positive 3 times 4, so that makes it positive 12. So in this case, in this case, what we have here is something like 3 minus 12 over x squared plus 4. Okay, and then we can just simply perform here the operation necessary, so that is 3 times x squared plus 4, and then minus 12 all over x squared plus 4, which gives us 3x squared, and then this 3 times 4 is 12 minus 12, so this cancels out, and then leaves us the whole integrand here, that is 3x squared over x squared plus 4. So our answer here is correct. Now for this problem, what you can see here is not a fading integrand because it's something like a combination of 2x plus 3 divided by this denominator, which is a little complicated because of the squared sign. Now, what I'll be doing here is that I'll be dissecting this into two terms. So I have the integral of 2x, and then the square root of x squared plus 4, and then I have dx, and of course plus 3 times, or you could just write the integral of 3 dx. So that is dx over the square root of x squared plus 4. Okay, so this latter term, we can actually see that this has a fading integrand in your table. So you can actually use the arc sine hyperbolic inverse of your hyperbolic function. So this gives us the inverse hyperbolic, hyperbolic sine inverse of u over a, so that is actually x over 2. And then of course you just have to copy this constant here. So the rule is stated at I think that is 1 2 3 4 5 6 6. Okay, that is actually 6 from the rightmost column. Okay, so with that being said, so that is 3, and then the inverse sine hyperbolic of x over 2. Now that's actually u over a, and u is actually the value of u is equal to x, and then a is actually the square root of 4, that is 2. So that is the antiderivative of the last term. Now how about this first term? Now if we want to look closely here, we can actually rewrite this in terms of something like 2x times x squared plus 4 raised to negative 1/2 dx. And what I'm trying to pinpoint here is that this integrand, if you will be looking closely at this 2x, this is actually the derivative of this x squared plus 4. And when you have this, let's say f of x multiplied to g of x, wherein this f of x is actually the let's say the derivative of g of x. Now knowing that this is something like the parent function, now we can just integrate this. So we'll be having x squared, oops, let me just use another color here. So what we'll be having here is x squared plus 4, and then this one is negative 1/2 plus 1, so that makes it positive 1/2. And then since you'll be dividing this by 1/2, that makes it multiplied to positive 2. And this is actually your answer already. Now you might be thinking, why did this happen? I mean, this looks very simple compared to this expression. Now let me show you the derivative of this expression just to check what happened here. Now if you want to try to check on the derivative of this function, we can say that you just have to copy the constant, and then this one is power rule, so that's 1/2, and then x squared plus 4. Okay, then 1/2 minus 1 would be negative 1/2, and then the derivative of what's inside here by chain rule, so that is 2x. Okay, now this cancels out because that becomes 1, and then as you can see here, that is the 2x that is similar to this 2x right here, and then we have x squared plus 4 is a negative 1/2. That is the exact first expression here. That happened because something like the parent function is differentiated, and the result of that is from the chain rule itself, you have to have this 2x, and that is the very reason why you have just to integrate this x squared plus 4, and you don't have to try to find fitting integrand anymore, because this is actually a fitting integrand itself, in a way that if you have this kind of expression wherein f of x is the exact derivative of g of x, or you can just simply write this as f of x times the something like this, you can actually perform integration itself, wherein you just have to consider this f of x. Okay, so this is your final answer for this letter G. Now let's have this next problem. So I've modified this item h. So as you can see before, it has squared and then x to the fourth. Now I need to modify that because basically we can integrate that. So let's use x and then x squared here. Okay, so in this case, for the first term, as you can see right through here, I'll be factoring out 7 here so that it is left out with the x over x squared of 9 minus x squared. And basically, if you be checking on all the rules, you can see a rule that looks similar to this. Okay, but we'll just leave it for later. And then this one can be rewritten in a way that is plus something like the integral of e raised to ln of a raised to x, because that's a property of our logarithm. Then also the x plus the integral of e raised to ln of x raised to a, that's dx. And then finally the last one will be plus the integral of e raised to ln of a raised to a dx. Now to deal with the first expression, I have factored out 7 just to leave the expression right here that looks similar to the derivative, the antiderivative of the expression after the inverse tangent hyperbolic of x over a, that is the secant hyperbolic inverse of x over a. Now this makes the answer equal to 1 over a, so that is 1 over 3, and then the inverse hyperbolic secant of 3, I mean that's x over a, so that is let's just remove this. So let us use the absolute value of x over 3. Okay, and then this makes sense when this is the exact antiderivative when the expression at the dx is negative. Now we have to incorporate this by changing this to negative, and then we multiply this by 7. Now that we've already multiplied this by 7, which is the scalar multiple for this expression, now let's proceed with the rest of the expression here. Now for the first one, what we have is here is e ln of a raised to x. And remember, if we want to simplify this further, we could say that this is actually equal to a to the x, because this e raised to ln becomes actually equal to 1. So that makes this a to the x. And then this one becomes x to the a, and finally the last one becomes a to the a. So we can simply integrate all of these expressions based on the rules that we know. So we have to add the integral of a to the x dx, which gives us the antiderivative that is actually equal to a to the x divided by ln of a, because the derivative of a to the x, remember, is a to the x times ln of a. So that makes perfect sense by simply dividing the answer by the natural logarithm of a. And then for the next one, what we have here is x raised to a plus 1 divided by a plus 1. Okay, and then lastly, for this expression, what we have here is a to the a. And we know very well that since a to the a is a constant, then you just have to incorporate x at that expression. So that makes this a to the a times x. And finally, you have to add the constant of integration. You can just rewrite all of these in a simpler term. So this gives us negative 7 over 3, the inverse secant, hyperbolic secant of the absolute value of x over 3, and then plus a to the x over ln of a, plus x raised to a plus 1 divided by a plus 1, and then of course plus a to the a x plus c. So this is your final answer. And you can always check using differentiation. If you do that, you have to apply the differentiation rule for inverse hyperbolic secant. And sometimes you might want to express this in terms of its corresponding expression. Remember, we used to have the correct expression, I mean the exact expression using the natural logarithm for this inverse hyperbolic secant, but you don't have to do it. You don't have to do it as long as it's not instructed to you. So let's just leave the answer as it is. Now for this now for this problem, if you'd be looking at the rules again, at the last rule for trigonometric function, you can see here the rule that is stated. The integral of cosecant x is actually equal to the ln of cosecant of x minus cotangent of x. So in that way, we could just apply that to our integrand here. But the thing here is, how do we apply it when we have this kind of function that is not just simply x? So what you have to do is to just use that rule. So in this case, our answer would simply be equal to the ln, or the natural logarithm, of our expression itself, which is the cosecant. So you just have to copy that, and I'll be using also the absolute value symbol. So that is cosecant of 3x plus 4, and then you subtract that with um, cotangent. So the trick here is that if you use cosecant, so that's something like you'll be using again the other one, which is something like again, so that's cotangent. So that's the trick here. That's cotangent, and then 3x plus 4. Okay, so now you can just add the constant of integration, but this one doesn't end here. Why? Because this one is 3x plus 4, and the rule that is written at your handout is actually for just a variable that is x. So what we have to do here is to think of this as being differentiated. So when we try to differentiate this, or this one, what happens that we need to differentiate the term on the inside. So that's how it works for chain rule. So with that being said, we need to something like do something that um, would change this chain rule to the original expression. And the only way that we can deal with that is to do the inverse of the operation that has to be done. So if the chain rule gives us a multiplier that is 3, then it is needed to have this multiplied by 1/3, because that makes perfect sense when you have to integrate something like this and then you'll be multiplying 3. So this one kind of makes this positive, I mean multiplier 3 divided by 2 itself. That's why it leaves us with 1, which gives us the entirely the same expression as the integrand. Okay, so this is basically your answer for this expression. Now if you're kind of doubting that it should have 1/3, I'll show you again how we can deal with this by taking the um, added derivative of this expression. So that's 1/3, and then this one is in the natural logarithm, so I'll be having this 1 over cosecant of 3x plus 4, and then minus the cotangent of 3x plus 4. Now I need to multiply this by the derivative of this cosecant 3x plus 4, and remember, this one is cosecant, so the derivative here is negative cosecant 3x plus 4, and then cotangent 3x plus 4, then multiplied with 3. Okay, and then again we have to do it for this one, so that's minus, this one is cotangent, so that is negative cosecant squared, and then that is 3x plus 4 times 3. So this 3 right here is the one I'm talking about that we can cancel out using this 1/3 expression. Now we can simplify this further because we can factor out here the cosecant term 3x plus 4, and then kind of this cosecant 3x plus 4 being factored out, it will be left out with this expression that is equal to what we have here is, so by the way, I use negative here, but remember this one is cotangent, so that is negative cosecant, so this one makes it positive. So we're left out with positive cosecant 3x plus 4, the one that is left out here from squared, and then minus cotangent, because that's the one that is left out, cotangent 3x plus 4. Okay, then you divide this by cosecant 3x plus 4 minus cotangent 3x plus 4, and then you add something like dx. So with this, we can cancel this out, and then we're left out with the original integrand for this problem. So that is how it works for this problem. And remember, these are easy problems because they are actually fitting integrands. As long as the integrand fits to the rules, then you can just simply use the rule and then integrate that so that you can um, obtain the antiderivative of any expression. Okay, so I think that ends the discussion about basic integration rules for fitting integrands. And for the next video, I'll be presenting the discussion about pattern recognition and change of variables. Okay, so thank you.